Oh, take a look at number 9. This is at the very end, and we're going to circle back and do one or two of those other ones that we left before. But for now, let's take a look at number 9. Number 9 says, find the equation of the tangent line at f of x equals 9 minus x squared to the 2/3 at 1, 4. So I'm going to take this all the way back to the start. We have asked you this a lot of times. I'll keep asking it because we need to be really good at this. If I ask you to find the equation of a tangent line, what are the two things you have to have? Point of tangency and the slope of the tangent line. What of those two things, which is the one that I just flat out gave you and you didn't even have to try? That's right there, isn't it? 1, 4. That's the point of tangency. I agree. And so that will take very little effort. All you have to do is look at it and say, that's the point of tangency. That's where the tangent line intersects the curve, right? That's that point of tangency. But we do have to find the slope. We'll have to do a little bit of work to find the slope. So what is the slope of the tangent line? What is that? What's another name for that?
Derivative.
The derivative, yeah, f prime of x. So I think to myself, well, where's f prime of x? It's nowhere, but I do have f of x. So how do I go from f of x to f prime of x? I'm going to have to use a chain rule because I got to do a derivative, right? So let's think about this chain rule now. Within f of x, it's composite, right? Something put into something else. We need to identify the inside part of the composite as well as the outside. What would you guys say is the inside part? Yeah, that's the part that's inside. And then, of course, the outside to something to the 2/3, right? So to differentiate this, I need to differentiate the outside first. So how do you differentiate something to the 2/3? What rule do you use? Power rule, yeah. So that 2/3 just comes right on down in the front, and the inside part just stays as is. And then what do you do to get the brand new exponent?
Minus 1.
Yeah, so 2/3 minus 1 is?
-1.
That's right. So there's the first part of the chain rule. But then what I've got to do is multiply by the derivative of that inside. And what's the derivative of that inside? That's right. So that's my complete f prime right there. And this is sometimes a stage where people will struggle. This is the slope of the tangent line at any x value. That's great and everything, but that's not what I want in the end. What do I want in the end?
The slope of the tangent line so you can get the equation.
At which point?
1, 4.
At 1, 4, at my point of tangency. So our slope of the tangent line only depends on x. So I could just say f prime of 1 equals, and here's some fancy arithmetic. 2/3. Well, 1 squared is just 1, and 9 minus 1 is 8. And then -2 times 1 is -2. So without a calculator, does anybody know what 8 to the -1/3 is? 1/2. Well said. So 1/3 means cubed root, negative means flip it. So you're right on the money with that, Santi. So we get 2/3 times 1/2 times -2. And this all ends up being -2/3?
Would that be on a note calculator?
Yeah. -2/3, yeah. So let's go over the details on that. 8 to the -1/3. So let's deal with it in two parts. Doesn't a negative exponent tell you to flip the base to the other level? So you could transform it like this and say it's 8 to the 1/3, or sorry, 1 over 8 to the 1/3. That's dealing with the negative. And then what about the 1/3 power? Cube root, right? So this would be 1 over the cubed root of 8. And the cubed root of 8 is 2, so it'd be 1 over 2. You definitely can break it down like that, but I would say for sure you could be able to do that without a calculator. Okay, so let's not lose sight of the fact of what that is. It feels like we've accomplished something and we're done. We have accomplished something, but we're not done. What do we do with that -2/3? What is that? It's the slope of the tangent line. So, as you guys know, I like point slope. I would just write y minus 4 equals -2/3 times x minus 1. And I would call that just fine. What do you think?
Love it.
Any questions? We continue to go back to tangent lines, don't we? All the time. We'll keep circling back around, and if you're not already really good at them, you'll eventually get really good at them. I think you're making progress for sure. Do you guys have any questions? Now's the time. Something I said, something I did, unclear. You guys jumped in there with the whole 8 to the -1/3. Hope we cleared that up. Anything else? Okay, well, let's go backwards again then. I think it's like numbers 5 and 6, I want to say. Let's go back and see. I don't remember. There's a couple we didn't do. And let's do at least one of those.
We did 3, 4, 6.
3, 4, 6? Okay, 3, 4, 6. How about, let's do 6. Let's do 6 for now. And maybe we'll come back around and pick up 3 and 4 a little bit later. Maybe at the end of today, or maybe we'll do it on Wednesday or something. Okay, number 6 says, it says find the derivative, right? I think that's sort of the general instructions for this section. And I got a lot going on, right? It says f of x equals tangent of g of x, so that's composite, plus g of cotangent of x. And it never really tells us what the rule for g is. It just names it, g of x. And so we'll see how that goes when we come down to finding its derivative, because we're supposed to find f prime. By the way, this is a pretty classic case where you've got one equation with 2 different functions. You've got f of x and g of x, 2 different named functions. This is why I want to be really, really careful that we don't just think of every function as f of x. I know it's tempting to think like that, but there could be f, g, h, l, whatever. We want to be careful that we think of them as being different. Okay, so for this first one, tangent of g of x. Clearly composite, right? Something has been put into something else. What's the inside function for this first term? G of x is inside. Outside would be tangent. So if we're going to be differentiating, we need to differentiate the outside first. What's the derivative of tangent of whatever? Secant squared. So it'd be secant squared of g of x. But then I've got to multiply that by the derivative of that inside. In this case, that would be g prime. Good. Very well done. So why don't I leave you guys to handle the second term, and we'll try to put it all together here in a second. So work together, work on your own, see if you can figure out what that would look like there for the second term. Ready, go. What would you say? Somebody from Brendan's table over here. What would you guys say for the second term is the outside function? G of something, right? Yeah, G is the outside, making cotangent the inside, right?
Yes.
Okay, so this can be a little uncomfortable symbolically, but I think it's good to practice. What's the derivative of G of whatever? G prime of whatever it is, right? So I'd say, yeah, I like that. G prime of cotangent of x would be the derivative of the outside. But then I've got to multiply by the derivative of the inside, which is a little more clearly spelled out, right? It's cotangent of x. So what's the derivative of cotangent of x? Hey, there we go. And I think we stop right there. We open both boxes, essentially, and we're good. Any questions, thoughts, comments? It's a little bit different, I realize, but hopefully that works for you. So that leaves us with 3 and 4. Let me just do a little bit of looking here, because I'm gonna decide what I want to do. So I know what 3 and 4 are. Let me just look at this really quick. Yes, ma'am.
If it's negative cosecant of a negative number, does that make it positive?
If it's a negative cosecant of a negative number, do the negatives cancel to be a positive essentially? No, they don't. So like if you have, I think I'll do one of these. So if you have, I'll just write this out here. This has nothing to do with number 4. If you have negative cosecant of negative 2 pi, you cannot say necessarily that equals cosecant of 2 pi. It might equal it. I don't know if it does or doesn't, because you know sines and cosines and all that stuff, eventually ones and negative ones and all that. But you can't be like, hey, boom, boom. Because this is an input. This is just something making the output negative.
Okay.
They don't necessarily interact like that. Great question.
But if you timed that, the
If I-
entire thing by a negative number would be positive.
Sure.
Okay.
But the input would still be negative.
Yeah.
Yeah.
Okay.
Yep. Okay, let's do number 4, and I'll save that other one having to do with the tangent line. We'll save that maybe for Wednesday or something, okay? So let's do number 4. Number 4, once again, the instructions are to differentiate. And this is going to be one of our first kind of combination rules, okay? So I want you to think about this ahead of time. Let's identify the inside and the outside like we've been doing. It's clearly composite. What would you guys say is the inside function?
T squared over t cubed plus 2.
And very importantly, that whole thing is
Ins.
a quotient.
Okay.
So whenever, no, think about that. If it's a fraction, right? So, quotient was right, whoever said that. So whenever it comes time to do the derivative of the inside, you're going to have to do a quotient rule, aren't you?
Yeah. Heck yeah.
Yeah, so this is going to be an interesting combination. Well, that's the inside. Isn't squared the outside? So here we go. Let's see how this works. If I have to differentiate the outside first, how do you differentiate something squared? What rule do you use? Power rule. Okay, so the 2 just comes down in front. The insides are just left as is. And then, as before, you subtract 1 off the old exponent to complete the power rule. 2 minus 1 is 1. Obviously, you could write that or not. It's the same thing, right? So there's the derivative of the outside with the inside still hanging out in there. But then I've got to multiply by the derivative of the inside. And that's where identifying that that's a quotient earlier will be very helpful. To differentiate a quotient, you got to use the quotient rule. So the quotient rule is that low d high minus high d low over the square of what's below. Is this making sense? Okay. So low would just be t cubed plus 2. D high would be 2t minus high, t squared. D low is 3t squared, all over the square of what's below. T cubed plus 2 quantity squared. So low d high minus high d low over the square of what's below. So really, honestly, that second part, this part is old, something we've done before. But it's within a combination with a chain rule, definitely makes it feel a little more complicated. Andy, go. So let's talk about that. So, are you guys is it the little murmur about like, oh my gosh, like how scary that is, right? So do you have to clean that up? If the free response, no way should you do that. You should just leave it just like that. It would be foolish to do any cleaning up, to be honest, on a free response. Multiple choice, I'm going to ask these in certain ways. Believe me, it's not going to be about like, can you do crazy algebra in like 30 seconds? It's not about that. It's about, do you understand the calculus? So there are ways to ask questions like this that we can get to those ideas without making you do a bunch of algebra gymnastics. That makes sense? For instance, I could ask you what f prime of 6 is, and you could do some plugging in, and it would work out pretty nicely, perhaps, maybe f prime of 1 or something. That way I could test to see how you're doing without getting this crazy-looking answer. I mean, there would be all kinds of things we could do. That would maybe be one of them. But please don't stress about having to clean that up a whole lot. Okay? It's pretty rare. Pretty rare you'd have to do anything like that.
Did you ever make us do the second derivative of that?
I really can't make you do anything. No, seriously, if you haven't figured out that, I can't really make you do anything. I could ask you to do that, but I think that would be such an exorbitant amount of time that I don't think I would. Because that would just be like, honestly, I would allot like minimum 10 minutes to do that. And to think of a quiz taking like, say, 45, 50 minutes, that's like 25% almost of the quiz on just that. Feels like a lot. So if I wanted to see you do something like that, I'd make it simpler enough to where you could do it quickly versus all of that. You could clean this up. I mean, you could do some cleaning up like Andy asked. You could distribute the two things that could be distributed and add some like terms, and it would simplify it a little bit. But it would still be pretty complicated.
Okay.
Because then it would be, by the way, if I asked you to do that, what would be the overall rule?
Quotient.
No. Product. Overall, isn't it a product? Isn't it something times something?
Oh, I was just looking at this.
So you do
Yeah.
quotient.
So the overall rule would be a product. So you'd go 1, D2, and when you did the D2, there's a big quotient rule, right?
That would be the worst.
Plus 2. Now think about this, you do 2, that'd be just that nasty thing on the right. But then when you did D1, wouldn't it just be the quotient rule all over again?
Yeah.
So yeah, it would, I don't know if your paper would be wide enough to contain it, so I don't think it would be.
I think I'd just give up.
You'd have to, oh, please don't say that. That's two times you said that.
You're gonna break his heart.
I'm going to start believing you here pretty soon. Please don't. Okay, move ahead, please. I'm going to help you out with some of the video material. So I definitely don't have what I said in the video memorized, but here's what I would like to say about this. Do you remember how I told you that we've been doing the chain rule ever since we started doing derivatives? The truth is, from here on out, everything's going to involve the chain rule. Like that will be the one consistent thing that we got to consider. Almost everything we do, we got to ask ourselves, what's the derivative of the inside? That's going to be a part of everything we do. It's not going to be just one section in the book where like, oh, good, the chain rule is over with, let's move on. I know that it's easy to compartmentalize like that in other classes. Here, the chain rule will weave its way throughout everything we do. Honestly, it really will. And so we're going to keep going with that. So guys, listen carefully. This is the video material, and I definitely goofed, and I had this due tomorrow morning. You had to choose between yesterday and Wednesday, and if you chose Wednesday, whatever, I get it. What were you supposed to choose? It's my mistake, so I'm going to fix it. So make sure you pay close attention here. This will be kind of the video material. So everything we've done so far has basically been like y in terms of t, or y in terms of x more commonly. We haven't had anything that was really that messy yet as far as x's and y's, or maybe y's and t's or something like that. And so, so there are going to be certain functions, you'll see them here, that are either really difficult to write explicitly, which is solve for y, or maybe impossible. We call these functions implicit functions. And you've seen these before. You probably didn't call them implicit functions. But in this case, implicit differentiation, I hope you're hearing me, is not only the way that I would ask you to do it, it's the better way. It's faster and it's way easier. It really, really is. So let's go and talk about what these symbols mean. dy dx means this. And I want you to get this. I think probably if I would have asked you this in the past, you would have said probably the derivative.
Yeah, I would say f of x. Or
F prime of x? Sure. So dy dx means this. Derivative of y with respect to x. So WRT is actually an accepted acronym for with respect to. So that means the derivative of y with respect to x. And it's actually where the symbol comes from. ddx of y. So ddx means the derivative with respect to x of whatever comes next. And obviously the thing that comes next is y. This is where we get the symbol for dy dx. So dy dx means the derivative of y with respect to x. And it's at this point you might say, well, isn't that sort of redundant? Isn't everything y in terms of x? And the answer is no, is not. You can have y in terms of t, you could have L in terms of t, you could have t in terms of x. You could have all kinds of crazy arrangements how things go. And if you understand that the chain rule is kind of the overarching principle over all of it, you can do it. I'll get a little bit silly here at times as needed. I can't remember if I get silly in the video. You said you watched it. I don't remember if I got silly or not in there. We'll see how it goes. So, when you've got an expression like that, ddx of x cubed, what this is saying is do the derivative with respect to x of x cubed. This would be, as I put up there, proceed as normal. So wouldn't you just use the power rule? You'd say ddx, derivative with respect to x of x cubed. Well, you just go 3 times x squared. But do you remember, earlier this, or I guess it was later last week, I said you could treat that like it's composite. Couldn't you say x cubed is really x cubed? Like the x is the inside function and cubed is the outside. Now, if you can get this, this is going to make this implicit differentiation thing super duper easy. So really focus and ask a question if something confuses you, or get it and be happy with it, right? But really focus. Don't just let this float through your ears and over your head.
Why would you be able to put the pen, like if it's not there?
But so I guess I would say, I would counter your question with, what rule am I breaking? No, I'm not trying to cause a fight or anything. I'm just saying, like if I had like 5.
It would be the same.
It's the same thing. Yeah, same meaning, but what I'm trying to do.
Would the derivatives be different?
Well, let me show you. So if I look at it as if it's a composite, and I realize it's very trivial, right? You'd say the inside is x and the outside is something cubed, right? So how do you differentiate something cubed? Power rule, yeah. So we'd say this is equal to 3 times the inside squared, right? Making sense? Now the inside we know is x. But then wouldn't we multiply times the derivative of that inside? And what's ddx of x? 1. I'm going to write it like this. ddx of x, which we could further simplify or refine to be dx And what's dx dx? 1. Yeah, d dx of x is just 1. And so we would typically never go through all that. We would just write it as 3x squared. But you know that it's 3x squared times 1 technically. Times 1 just being that chain rule factor. Now you might ask, and let me Nick, is it okay if I roll ahead here? Because you might at this point be asking, what in the heck is a point? Why did we go through all that pain and suffering with the whole dx dx thing and the one I'm about to show you? Does that make sense? So check out the next one down below. This is where it's different. And if you could sort of hang with me on that upper line, this next one hopefully it'll come home for you. So notice that it says d dx of y cubed. It's not d dy of y cubed or d dx of x cubed. The fact that this x and this y are different variables makes all the difference in the world. We're doing d dx of something that involves a y, something involves not an x. So here's how this would go. It will go the same way, except something's going to kind of show up differently at the end. I'm going to say that this is really d dx of parentheses y cubed. And like before, I'm going to sort of imagine a little bit that y cubed is really composite, right? So the inside would be y, and the outside would be cubed. Let's see how this goes. I'm going to say, in order to differentiate this, I have to use the power rule. So this would be 3 times input squared, right? What's the input? And it's very important that that's a y, not an x, because it's different. That's why it's so important. Now, here's the chain rule factor. Don't I have to multiply by the derivative of the inside? d dx of y, is that 1? No. It is not. d dx of x is 1. I'll give you that. But d dx of y is different than x. They're different variables. So this would be d dx of y. And if I clean this up a little bit, it ends up being 3y squared times dy dx. And that right there is the result of doing d dx to y cubed. So I mentioned earlier, this can get very, very silly. But the whole point of this silliness is simply that the dd whatever, in this case it was x, like the letter, the variable there, matters. It's not just some generic variable which, just do a derivative. If it's d dx, that has a different meaning than d dt. If it's d dt, that has a different meaning than if it's d dy, which has a different meaning if it's dd smiley face. So for example, let's say if I said, all right, let's do, I'll just make up a new one. Let's do dd smiley face of y to the 4th. Well, you'd look at this and you'd say, all right, well, y to the 4th, we could think of that as a composite. And to differentiate the 4th power, it's just a regular old power rule like we've done before. So this would be 4 times something cubed, and the something is a y. But you'd multiply by the chain rule factor. What do you think the chain rule factor would be here?
dy d smiley.
Yay, dy d smiley face. Okay, so what do we do with that whole dy dx or dy d smiley face? That's what we'll talk about here in this section, okay? Let's do one more here real quick. I'm going to just clean this up a little bit. But remember, that extra factor of dy dx or dy d smiley face or whatever, it comes from the chain rule. We're just doing a chain rule. Okay, so d dx of parentheses xy squared. What do you think the overall rule here is? Say again? Product. Do you see that it's x times y squared? Easy thing to miss. Easy thing to miss. So let's do this. We're going to go 1. What do you guys think your 1 would be? X. Yep, agreed. So there's 1. Now let's be super careful. What do you think d2 is going to be? So 2y times, we'll say again? Times dy dx. You're right. So did you notice that we did d dx of something that involves a y? So if you do d dx of something that involves a y, then that chain rule factor of dy dx will show up. It won't disappear like that dx did as a 1. It'll show up. So there's my 1d2 plus 2, which is y squared. What's d dx of x for my d1? It's just 1. So I'd leave it as is. What are we going to do with something like that? That's kind of what comes next. We're just practicing a little bit of how do you do d dx. Okay. Any questions? Yeah, oh yeah.
Why is it plus y squared?
So it's so this right here, come on. This is 1. This whole thing is D2. This is 2. And then D1 is 1. So because it's a product rule. I didn't write the times 1 because, y squared times 1 is just y squared. But it comes from that product rule, like the second term of the product rule. Yes, ma'am.
So then have the thing, what is the point of doing this to find, dy? What is the point of doing
In the end, right now, it's going to be to find dy dx. We'll do some other stuff later with it, but the point is going to be right now to find dy dx. Yep. Yep. Good question. Anybody else? All right. So then we're going to do this one example here. So you got some steps right there. I'm not hyper concerned about reading those steps out loud. I thought we could just do one of these. We'll do a couple of them here, kind of see how this goes. So take a look at number 1, please. So for numbers 1 through 2, it says use implicit differentiation to find dy dx. So you do have options here. If you wanted to, you could solve this one for y. And the problem is you're going to get a plus or minus in there. You guys know what this graph says? It's not a circle. If it was plus, it'd be a circle. Say again? Not an ellipse. There's 2 more. Hyperbola. Yeah, it's a hyperbola. So you guys know how the hyperbolas work. Like if you solve for y, don't you have to pick like the upper half or the lower half? The plus or minus comes into play. It'd be a mess. It would make a definite mess if you solve this thing for y. So this is a case where implicit differentiation, I would say, is not completely necessary, but it's going to make this easier. So here we go. Let me show you, your question was good. Where are we going to use this? We're going to use it right here. So here's what you do. You are asked to find dy dx. So keep in mind that finding dy dx means do ddx. Like it's saying do ddx to everything, and not ddy, because if they want a ddy, they'd ask you for something d whatever dy. So if they say find dy dx, that means you need to do ddx to everything. Yes, sir?
What is doing ddx?
So it means find the derivative with respect to x. Differentiate with respect to x. We'll do it right here. So check this out. Well, so it involves, so Santi, the quick answer is it involves like the power rule, derivative of sine or cosine.
Set this equal, can you just say x squared minus y squared minus 25, and then
That's not going to make too much of a difference. Look, can I show you? You guys are do we do this? Can I just show you what we do? Okay. So doing ddx means, it's another way of saying, if I told you, if I said, hey, Santi, can you find the derivative? You would say, yes. I could ask you the exact same question by, can you do ddx?
Why wouldn't you say dy dx?
Well, so dy dx, okay. So I think I've said this before, I think, maybe it was the other class. Dy dx is a noun. It is it's a thing. You find dy dx, it's the slope of the tangent line, slope at a point, all that stuff. ddx is not a noun. ddx is an action. ddx is saying, find the derivative, differentiate this with respect to x.
Can ever be dy over d?
No.
Okay.
No. It's just what the symbology means.
Could it be dy?
It could. It could be ddt, dd smiley face.
Can we not use the power rule and stuff like that?
Yeah, you sure can. But then your chain rule factors are going to be
With the
other
x,
stuff.
With whatever's not y.
Exactly. So Santi, are you okay? Because you're like, what in the heck is do ddx? Well, no. Listen, I am not okay with just the, I don't get it, just leave me alone. That's that's the vibe I'm getting, am I right?
Yeah.
Okay.
It's the first thing he hasn't gotten.
Honesty is the best part.
I am not telling him to not be honest. I'm actually telling him to be honest because he's almost telling me to move along. And I'm saying, no, I'm not going to move along. So ddx is telling you to do something. Dy dx is the result of doing that thing. So for instance, if we had this would be an old one. If we just had y equals, 10x to the fourth or something. And I said, do ddx or find ddx or differentiate with respect to x. That's what it really means. then you'd say, all right, well, d dx of this whole thing, well, d dx of y is just dy dx. Because it's the meaning, no, listen, it's the meaning of the symbol. Like now we're getting down into the nitty-gritties. We're almost down to this, and I'm not trying to trivialize what you're saying at all, but it's almost like me saying, hey, that means plus, and you saying y. And I got to come back at you and say, it just means plus. It just means plus. So like, it's I'm not trying to like over-trivialize it for you, but this symbol right here literally just means do the derivative with respect to x. And there's not really a y to that. It's just that all mathematicians have agreed that d dx means, just like we all agreed, like if you said, you know what, I've decided that means factorial. We're all going to be like, well, that's cool for you, but nobody else thinks that. Yeah. Like we've all decided that symbol means addition. So it's been decided by people that are smarter than all of us combined in the history, like Newton and whatever, that this means find the derivative with respect to x. And we kind of just have to say, okay, cool. Does that make sense? Yeah. There's not really a y.
Wait, can you finish that one?
Oh, sure. So then you'd say, you'd have to use the power rule.
Sorry, I just wanted to see
You'd have to use the power rule. So 4 times 10 is 40. It'd be 40x cubed. But then it would be the derivative with respect to x of the inside. And what's d dx of x? 1. So we've done that chain rule factor all the time. We just never wrote times 1 at the end of all of our derivatives. Okay. Let me do this one right here. This might be a good connector for you. So check this out. Here's how you find dy dx for number 1. Did you notice that it's not y equals anything? It just jumps in, it's like x squared minus y squared equals. There's no y equals all by itself, right? And isn't that very different from what we've done? Isn't that very different from what we've done? Yeah. Oh, I need you to focus, guys. I can tell you're struggling.
But you could just
fight it. Come on. You could, but it's going to make more of a mess because you'll get a plus or minus. And how do you deal with that? It's going to make a big mess.
You're going to have like 2 parts. These are right.
Exactly. Exactly. Can I just do this one? I feel like we keep on doing the what are we going to do next, and I'd like to just do the do next, and then I can still answer questions. But let me just show you, okay? So here's how you do this. X squared minus y squared equals 25. We're going to, because it says find dy dx, we're going to do d dx. We're going to find the derivative with respect to x. So I just usually note that by writing d dx. Okay, so I'm going to do d dx of whatever shows up next. So let me just hear your thoughts here. What do you guys think d dx of x squared is? That's the first term. 2x. It's 2x. 2x times 1 technically, but we're never going to write that. We'll just write 2x. Minus. I'm not going to ask you what the derivative of y squared is because that's too generic of a question. I'm going to ask you what's d dx of y squared, and what would you say?
2y times dy dx.
Hey, there we go. Does that make sense? I can see that it didn't totally make sense. So let me show you this. Listen carefully. No, listen, you've got to focus in here. The d dx of x squared is 2x, and I'm going to write it like this, dx dx. The derivative of the inside, which in the first term's case is x, right? So d dx of x minus 2y, again, times the derivative of the inside with respect to x. Do you see how it's consistent?
I think if we go back to the first part when we put it in the parentheses and it was parentheses.
Sure, we could do that. That just gets super gangly.
Explain it more, I think.
I get it.
Just a few more minutes.
I understand. Let me finish this really quick because I'd like to get you to a conclusion, and we can go back. I think that's a good idea. What's d dx of 25?
0.
A 0.
d dx of a constant, dd whatever of constant is just going to be 0. Oh, Young, did you have a question? Looked like your hand was up, maybe.
So the inside is what we did with the parentheticals at like the very top of the page?
Yeah, we're still doing the same kind of thing. So what I'm looking at, I'll go back to that if you want. So,
But to write as a final answer, do you still need to do d dx?
yeah, so we're really struggling with this. Just I feel like I need to kind of put out some fires with little questions, and I'm not getting to the end, and maybe that's my mistake. I'd like to get to the end, but let me go back, because I see you're like, well, where does this come from and all that stuff. So what if we looked at it like we did earlier? What if we looked at what if we looked at this as the inside and this as the inside? We're doing that, like, put those in mentally, right? I can tell you right now, I am not going to do that all year long, and I don't think you are either. We're just going to see that a little bit quicker, but that is what we're doing. Okay. So we're going to say d dx of all that. Now I'm going to finish. So it's 2x times dx dx minus 2y times dy dx equals 0. What do you think?
Just finish it.
Okay, what's dx dx? 1. So this just gives us 2x minus 2y. dy dx is just dy dx. Now the end goal, and this is what you were asking for. Remember, the end goal is to find dy dx. We could just solve for it, right?
Yes.
So what I would do is I would subtract 2x from both sides. That's going to give me negative 2y dy dx equals negative 2x. And then how would I finish this? Divide by negative 2y. Because remember, the goal is to get the dy dx all by itself. So I divide by negative 2y and divide by negative 2y. This gives me dy dx equals, well, the negative 2's just cancel out. We get positive x over positive y. So in other words, this is a hyperbola, like we said at the start. So the slope of a hyperbola, think about how crazy this is. The slope of a hyperbola is simply the x-coordinate divided by the y-coordinate.
Is that true for all hyperbolas?
Yes.
Oh, wow.
As long as it's centered at the origin.
Gotcha.
Yeah. Pretty interesting, right?
I don't like
Not that you would think, not that you would just like jump to that conclusion. It's kind of interesting. This pattern will hold for sure. Okay, so where are we at? This is basically the intro video. There's more to this. Yes, ma'am.
So if you're trying to find an equation, like,
What do you mean find an equation?
because you got slope of this,
Right?
and you want an equation of like the tangent line.
Oh, sure.
You would put like the point of tangent.
I would need to give you a point of tangency, which I have not. So yeah, you really couldn't find the slope of the tangent line. But yeah, if I said at, when x equals 1 or something, I'd have to give you a little more information. But then yeah, you could just plug stuff in where it goes. Point of tangency, slope of tangent line, boom, tangent line equation. True.
And there could easily be like numbers still in the, like it could, like if it had just worked out differently, it could have been like 2x over y, like dy over
If
dx equals
oh
2.
sure, yeah, totally. If it was like not a hyperbola, yeah, totally. Okay. So I feel like this might be one of those cases where a little bit of repetition would actually go a long way. So let's do another one. I think there's one that's like similarly. Do I want to do that one? I don't know if I want to do that one. Let's do.
I saw the word quadrant. That's crazy.
Quadrant, scary word. I don't know. Let's do 2. I think 2 will be good. Okay. So before we get too much into the details to this where we'll finish, but before we get into all the details of 2, look at it kind of carefully and think, if I were to differentiate this, what's going to happen? What might just naturally jump up? Product rule. Do you see them? How many of them? 2 product rules. So this right here is a product, so we'd have to use the product rule. This right here, also a product. So we're going to have to use the product rule. That's kind of our overall rule. Yeah.
So if we're gonna find like ddx of this,
Mm-hmm.
how do you know that it's telling us to find ddx of this? Like,
Great question. So yeah, without
Like, how do I know it's not
let's look back at the instructions. Yeah, because it could be dd whatever. It really could. If you look back at the instructions it says for numbers 1 through 2,
Okay.
find dy dx. And so because it says find dy dx, that's where we get our, because if I didn't give you those instructions, you'd have to be like, well, what am I supposed to do with this? And that's a very legitimate question. You have to be like,
Yeah. I thought
I don't
you were
know.
just looking at the equation and knew.
no. Yep, definitely have to give you the instructions. Good question. Okay, so let's see here. Number 2, the goal is to find dy dx, as you can see in the instructions above. So if I'm going to ask you to find dy dx, that means the very first thing we're going to do is we're going to find ddx of the whole thing. That's going to be our first step on these. So I'll just rewrite real quick. X squared y plus y squared x equals negative 2. And I'm just going to do ddx, the derivative with respect to x, of the whole thing. And the reason why I'm doing that, again, just circle back around to Anna's question, is because I was asked to find dy dx. Okay, so as we pointed out earlier, got some product rules here. Let's go through this slowly, and if questions come up, let's make sure we ask them. For this first one, would it be okay if our 1 is x squared and our 2 is y? For the 1d2 plus 2d1 routine? Yeah? Okay, so what's 1? X squared. What about d2? What's ddx of y? It's technically 1 dy dx, right? So I would just write dy dx. derivative of y with respect to x.
How do you do a dx then?
Say again?
How do you do a dx then?
So,
I just don't see the point in having a d by dx in there if it's just 1. Does that make sense?
when you say it's just 1, you're saying the derivative of y is 1?
It's just 1.
So here's where we get into the wording is quite important. If I say the derivative of y is 1, I need to be really clear. Is it the derivative with respect to x that I am finding, or is it the derivative with respect to y? So I would say this. This is going to be off to the side. This is something related, but not directly to this whole thing. If I said d dy of y, the answer is most definitely 1, and that's it. If I said d dx of y, the answer is 1 times the derivative of the inside. If I said d dt, which is something we'll do later, of y, that would equal 1 times the derivative of the inside with respect to t. If I said d ds for Santi of y, that would equal 1 times dy ds. Do you see the pattern?
Yeah.
So technically, this would be dy dy. And what's dy dy? 1.
Cancel out.
It's 1.
Okay.
Yeah.
Keep going. I just finished the compliment.
Okay. Yeah, I feel bad, Santi. I feel like you feel like I'm being antagonistic towards you, and I'm really
No,
not.
it's okay.
I'm really not. I really want to help you.
It's all good.
No, if you're not getting it, it's the opposite of all good. Okay, I'll keep going. So that's 1d2 plus 2. What would you guys say your 2 is? No. 2 represents the second factor. So wouldn't 2 be y? So 1d2 plus 2 is y. And what's d1? What's d dx of x squared? 2x. With no extra d anything whatever, right? Because we're doing d dx of an x term. So 2x is right. So 2xy or y2x, same thing. So right there, that's 1d2 plus 2d1. Now, I've got to add to this the product rule that I am circling in green. So again, are you guys okay with 1 being y squared and 2 is x?
Yes.
Okay, so what's 1? Y squared. Because we're just doing straight up 1, right? So 1d2 plus 2d1. So there's 1. What's d2? What's d dx of x? 1. Cool. So there's 1d2 plus 2 would be x. d1, what's d dx of y squared? Flip your fraction. 2y times dy dx. 2y times dy dx. Notice how the dy dx only shows up when you did d dx of something that had a y. Do you see it? dy dx doesn't show up just because we say, hey, let's throw one of those in there just because it should be in there or something. dy dx only shows up when you did either d2, which is right there, or d1, which is right there. That's the only time dy dx shows up because it comes from the chain rule. Okay? What's d dx of negative 2? 0. Okay. I'm going to clean this up a little bit because we have to get the dy dx's by itself. What follows is a little bit of algebra. So I'll write it as x squared dy dx plus 2xy plus y squared plus 2xy dy dx equals 0. So I just cleaned it up a little bit. Just got things in the order that we're used to seeing them in. So we got to solve for dy dx. Any suggestions on what would be a good first step? Yeah, move stuff around, right? So move the stuff that doesn't have a dy dx to the other side and leave the dy dx's on the left side maybe. So I would say that would be x squared times dy dx plus 2xy dy dx equals negative y squared minus 2xy. So again, I'm just rearranging. Like anything that has a dy dx, I left it on the left. And anything that didn't have a dy dx, I moved it over to the right by subtraction. Does that make sense? So now the last step is we got to figure out how to get that dy dx isolated. And there's obviously 2 of them. You see them hanging out there. How can I get those isolated? Factor, I heard, yes. So what I'm going to do is I'm going to factor that out. So that'll give me, let's see here. I'm going to come up all the way around to here. So when I factor out a dy dx, that'll give me dy dx parentheses x squared plus 2xy equals negative y squared minus 2xy. That hasn't changed. And after I've factored that out, what's my final step?
Divide by x squared plus 2xy.
That's right. Divide by that leftover stuff. So dy dx then equals negative y squared minus 2xy all over x squared plus 2xy. There's all kinds of temptations, all of them really bad as far as canceling. So let me just show you some of them. We all agree that this would be really, really bad, right? This would be even worse. I don't know. There's all kinds of crazy stuff that could happen here. Like this would be similarly terrible. There's nothing that cancels here. There's no common factor. So that's just it. Okay? Does it not have a negative 1? Where would the negative 1 be?
The 2xy, can't those cancel?
No. No, I'm saying that's bad news. You can only cancel whole factors of the numerator with whole factors of the denominator. And right now, the numerator is not factored.
Yeah.
So before you can cancel, you have to factor.
Okay.
And right now, it's...
We'd only be able to take out a y from the top and x from the bottom.
Yep, common y in the top, common x in the bottom, so still nothing would cancel. One more real brief note here, just a word of caution. You might find, like, if you're working with somebody, you might find that you got that answer in blue, and they might get this answer in red. And I just want to caution you on something. Do you realize that those two answers, the one in blue and the one in red, are totally equivalent? They're exactly the same answer. Basically, in the numerator, all of the signs have been changed. In the denominator, all the signs have been changed. So essentially, they multiply the top by -1 and the bottom by -1. It's the same answer. So just be aware that can happen, and it's okay. If you want, especially if you struggled with that at all, if you want to go back and rewatch that intro video, that might be a huge benefit to you. We obviously covered all the material, but seeing it and hearing it one more time might be helpful. Okay, so consider. No, it's my mistake. I'm not going to. Now, the other class, I did not make a mistake with their due date. So we'll go as normal there. But for you guys, I'll make that optional for you. But watch it if you need to, for sure. So have a great day. See you guys. Santi, how